All right, thanks everybody for coming, especially this late on a Friday. I know you probably all want to go home. So today's talk is going to be about enforcing authorization controls, essentially data level authorization controls using cryptography. So the agenda is really going to be talking about what the problem is that we're trying to solve, first of all. It's a very common problem. We're going to talk about some of the common solutions to the problem and some of the potential problems with those solutions. Then we'll talk about sort of a new cryptography-based solution. Not necessarily new, but I haven't seen too many people out there using it. And it is something that I've recommended a lot to some of our clients. We're going to do some performance comparisons of this approach with some of the existing approaches, see how it really compares. So not only looking at it from a security perspective, but also how does it actually perform? How does it scale? How does it compare to the other approaches? And then we'll do some conclusions at the end. So, what's the problem that we're trying to solve? In pretty much every application that we have out there that has user-specific data, we have this sort of problem, where we send some list of identifiers to the client. Could be credit card numbers, could be some sort of primary keys for emails or instant messages, whatever that might be. Some user-specific data in an application. The client has to select an identifier from the list and send it back to the server. And then the server returns more data based on that identifier. Now, what does the server need to do? Well, we want to make sure that user's data stays private relative to that user. So we don't want users to be able to send identifiers that belong to other people without detection. So I'm sure you've all heard of some of the incidents in the news over the past few years about people being able to view other people's tax returns or, viewing each other's emails, things like that. So that's the problem that we run into a fair bit. And that's what it often looks like. So you've got some sort of an account, credit card number, bank account, whatever that might be, or, like I said earlier, emails or anything that's user-specific. The server sends a list of identifiers to the client picks one, sends it back to the server. Now, of course, if I'm a malicious user, or if I see something in the URL, what happens if I increment or decrement one of those numbers? So that's the problem we're trying to solve. Now, how common is this problem? Since we're at an OWASP conference, let's take a look at the OWASP top 10. So number 4 on the list in 2007 was insecure direct object references. Now, what exactly is insecure direct object references? It's that you're essentially exposing some sort of a reference to an internal implementation object, like a file, directory, database record, and so forth. And if a user can change that, and you don't have authorization controls, users can access other users' data. So same sort of thing happened in 2010. Still number 4 on the list. In 2013, we all got smarter and the problem disappeared. Or not. Still number 4 on the list. So we keep running into this problem over and over again, right? So what do we do about it? First, let's take a look at some of the relevant attacks. Now, when we're talking about insecure direct object references, the main thing we're worried about is the thing at the bottom right there. A user who's potentially malicious is signed into the application and uses another user's identifier from their own session. That's the main thing we're trying to prevent. Now, there's a bunch of other sort of related attacks that are interesting to think about when it comes to direct object references. So some of these identifiers might actually be sensitive. So what if those identifiers get stolen because they're cached on the client? What if they're stolen via a cross-site scripting attack? Think about things like credit card numbers. Do we really want those things to be stolen? Probably not. Performing a cross-site request forgery attack using predictable identifiers. So this isn't really a CSRF problem per se, but if our direct object references happen to be predictable, then it makes CSRF attacks easier. We don't want to make CSRF attacks easier. So that's going to be sort of a secondary attack that we'll worry about and see if the various approaches that we'll talk about actually help make CSRF harder. So just a quick list of attackers and attack vectors. Just a summary of the previous slide. Now the attack vectors we're going to look at with every single solution to see how well it actually solves that problem. So here are the common solutions to the problem. I'm sure a lot of you might have seen these already. So we just exposed the direct object reference. So whether it's a credit card number, whether it's a primary key to a database object, we just expose it. But when we get it back, when the client sends it back, we do an authorization check. Pretty straightforward. Now, the problem with that approach is, well, we're potentially exposing sensitive identifiers. We've seen applications where, think of a corporate credit card program where you have a plan administrator. Do you really want the plan administrator to be able to see every single person's credit card number? Probably not. So direct object references with authorization checks have some problems. We'll look at them in detail in a second. Now, one of the most common ways to solve this problem is through indirect object references, where we don't actually expose the reference itself to the user. We create some sort of a mapping in the user session. And then we expose the indirect mapping to the user, and we'll take a look at how that works. The solution that I'm going to propose today is cryptographically protected references. So using cryptography to actually protect these references so they cannot be modified when they come back. And we can also protect their confidentiality. So let's go over the common solutions first. So direct object references with authorization checks. So let's take a look at what the client sees and what the server-side code looks like for verifying one of these references when it comes back, assuming that we're doing things properly. So on the client side, whenever we have some sensitive data, one of the things we'll want to do, as far as the things that are displayed to the user, we'll want to mask it. That happens a lot with credit card numbers, bank account numbers, and so forth. So what we display is going to be masked. But if you actually view the source of the web page, you have to expose the full direct object reference because the server has to know which object you want to operate on. So the client-side code sees the full direct object reference. No surprise there. What does the server have to do if it's actually performing the authorization check? It has to figure out which user corresponds to the current session from which the request is being made. It then has to grab the account ID that I'm trying to access. So the first thing is just from your session, so it's trusted. The second thing I'm getting is not trusted. It's coming from the client side. Then what do? We check whether the user has access to it or not. And where a lot of people make mistakes is they forget to check whether the user has access to that piece of data or not. So we have to do an explicit authorization check, and that's really important. You need to grab the user ID out of the session, and you need to explicitly check to see if that user has access to that object, which gets kind of tedious. Across a large application, every single time you're getting an identifier, you have to verify explicitly whether the user has access to it or not. Now, if we look at the attack vectors, well, we are not directly preventing using another user's identifier from your session. You have to do an authorization check. If you forget to do that, there's no inherent protection there. Once you pass the identifier to the client sends it back. There's no way for you to check, except with the user ID, whether the user has access to the object or not. With some of the other approaches, we will have a way to check, and we'll see that. Reading sensitive identifiers cached on the client, or by exploiting cross-site scripting, pretty straightforward. You can read those. You're exposing the sensitive data. And CSRF attacks really depend on the predictability of the identifier. Certain identifiers happen to be predictable, they're sequential, or something relatively predictable, in which case you're not really stopping CSRF attacks, not using your object references anyways. Of course, you might have CSRF tokens and so forth, but the references themselves don't help protect you. Now, this is one other solution to the problem, one that doesn't require explicit authorization checks. So we have sequential indirect object references. In this case, what does the client see? You probably still need to display a masked account number or some sort of identifier that's masked or hidden to the user, maybe an account nickname. But then the actual identifiers that you're sending back to the server, they're just sequential numbers. And you could imagine that that's just going to be a table in your session. So when a user logs in, you just create an array, and you've got 5 items in there. Now, what does the client do? It passes back one of the 5 numbers. You grab the account number from the request. You get the array from the user session, and you figure out which account number maps to one of those 5 numbers. Note that the authorization check is now being done implicitly. We don't need to grab the user ID and verify that the user has access to that object, right? It's straightforward. If you try to pass in -1 or 5, that object just doesn't exist. No need to do an authorization check. So that's a good thing. Makes things easier when we're coding. Now it mitigates 3 of the 4 things that we're worried about. You can no longer use another user's identifier from another session because, well, you're checking against something that's built in the individual user session. You can't read sensitive identifiers because they're no longer sent to the client. You can still use CSRF to perform sensitive transactions on those accounts, unless, of course, you have a CSRF token. Another approach is random indirect references. Now, this can be random in many different ways. I just used version 4 UUIDs. It can be any other form of random data. But instead of just an array, 0, 1, 2, 3, 4, I have just random identifiers. And the hash table mapping these to the actual account numbers is stored in my session. So the verification is very similar to with sequential identifiers. You're grabbing whatever the client sends. You look it up inside your session object. If you find a match, then you know the account number corresponding to it. Great. Mitigates everything, right? You can no longer use another user's identifier from your session. Can't read sensitive identifiers. You can't use cross-site request forgery to perform sensitive transactions because now these identifiers are highly unpredictable. So, aren't we just done? Why do we need another solution? So, what's the problem with random indirect object references? Well, there's a couple of big problems. One, there's a large memory footprint sometimes. Not for all applications, but for applications that are exposing a large number of references to the user, you have to build these giant tables in memory. And think about if you wanted to make your application server stateless for scalability. How much data do you have to share between the app servers? You have to share these giant tables you're building across the app servers. You have to write all that data to some common store. That's going to slow things down a lot. It's not very scalable. You could, of course, use sticky sessions, and then you don't have to worry about that. But if we did want to make our app server stateless, this would be difficult to do. So how do we solve that problem? Let's take a look at an alternate approach. What if we were to somehow cryptographically bind direct references to sessions? A couple of examples are shown there. These examples protect both the integrity and the confidentiality of the references. However, our options are integrity protection only, confidentiality only, or both confidentiality and integrity. For everything we're going to talk about, we're going to take a look at the last one, the integrity and confidentiality protection. So I hope that makes sense. There's many different ways in which you could use crypto primitives to do this. The 2 things I've outlined are AES in GCM mode, which protects both the confidentiality and the integrity of data. It's an authenticated encryption mode. Or I could just use a standard traditional encryption mode and combine it with a HMAC. And I essentially have a session key that I generate for each user when the user logs in, and then I use that session key for these crypto operations. This is what the client sees, and this is what the server has to do. The references become pretty big now, but it's sort of similar to the random indirect references, right? What you're seeing looks pretty random. What does the server have to do? It grabs the account number from the request, grabs a session key from your session, and then just verifies and decrypts. There's no need to do an explicit authorization check. If your crypto primitive is protecting the confidentiality and the integrity, more importantly the integrity, you don't need to do an auth check, which is great. Also solves all of these problems. So you can't use another user's identifier from another session. You can't read the sensitive identifiers, either via cross-site scripting or through client caching, and you can't use CSRF to perform sensitive transactions involving these identifiers. So great. Another possible solution, however, is probably more scalable now, because now the only state we need to share between our app servers is that one session key. We don't need to share these giant tables. So what about performance? How does this really compare with the other approaches? Are all of these crypto operations going to slow us down significantly? Is it really a viable approach? So let's take a look. So here's the setup I used for benchmarks. Why did I use this setup? I don't know. I just felt like it. I, for the most part, code in Java, so I use Java 1.7. For the crypto operations, I used the Bouncy Castle 1.49 library. For direct object references, I implemented two different versions. One without caching, so every single time you want to verify a reference, to do an authorization check, you have to go back to the database. For another approach, I implemented direct object references with caching, so now my authorization checks happen a lot faster. But I need more memory on the app servers. Sequential and random indirect object references, the only ones that I implemented were where they're stored in memory. So of course you could persist these things in the database to make your app servers stateless. However, I did not go down that approach, but you could imagine as far as some of the benchmarks, how they would turn out. I'll talk about those when I get to the individual ones. I used a local SQLite database. I know it's not necessarily a realistic setup, but it's just what I could get my hands on quickly. It created 10,000 users with 10 accounts each. And the benchmarking technique I used was to load the 100,000 records, load all of them, see how much time it takes to build the list that I'm going to send to the client for each one, and then verify just 5,000 of the references, because verification was just taking too long. I didn't want to verify every single one. And then I just divided by the number of references I was verifying to get my numbers. So let's take a look at the actual benchmark results. Now, this is the only graph where this is the case, but note that the x-axis does not actually start at 0. So the variation is actually a lot smaller than what it looks on the screen. So this is the time required to populate the initial list. So when the server is grabbing all of the references that a client should have access to, it generates that list, sends it to the client. How long does that take? Well, of course, the fastest thing to do is just grab that list and send it to the client. You're not doing much processing. That's going to be literally the fastest approach. If you're caching things, well, the whole caching logic is going to slow things down a little bit. Indirect references, sequential, don't really take much time. Indirect references that are random take a little bit of time to generate those random numbers. And the cryptographic references take a little bit more time. It's really only an extra 3% or so of overhead. So it's not a huge amount. But you do need to do those crypto operations to generate these lists. Time to verify these references. So now when the client sends the reference back, how long does it take to actually check to see if the user should have access to it? If we don't have any caching and we have to go back to the database for every single access control check, it's a pretty big hit. Now, direct references with caching, it's pretty quick. Indirect references, sequential and random, they're relatively quick because these ones are in-memory implementations. If they were database-based implementations to make our app server stateless, you could imagine that time would be very similar to direct references without caching. And finally, cryptographic references, the verification time does go up a fair bit. Now, one thing to remember is that I am actually using a local SQLite database here. For a real scenario where I have to go out over the network to connect to a real database, that number is probably going to go up. So the difference between direct references with no caching and cryptographic references may not be that much. Memory usage. Well, direct references with no caching, you don't need much memory, right? I'm not caching any of this stuff, so that's relatively straightforward. When I do start caching things, With direct references or with indirect sequential references, the memory usage goes up quite a bit when these references become random. Because, well, you need at least 28 bits of randomness for every single reference. So depending on how many of these you have, your memory usage is going to go up quite a bit. And remember, all of that data has to be shared amongst all your app servers if you want to make them stateless. Cryptographic references, you don't need a whole lot. You're just caching a 128-bit key in memory for every single session, not for every single reference. The identifier size, pretty straightforward. So how big are the identifiers I'm sending to the client? You probably saw those on the earlier slides. Straightforward, direct references with no caching or with caching, it's the same size. These are just identifier sizes that I chose. These were just random longs that are generated in Java. Indirect references that are sequential, they're going to be pretty small, especially if you're just indexing from 0. Random indirect references, the identifier size goes up. Cryptographic references, it goes up a fair bit. But now remember, the size of the references is bigger, but all of these references don't need to be shared amongst all the app servers that I might have. But with indirect random references, they do have to be shared. So here's a summary table of everything that we talked about. As far as the attacks that we're concerned about, there's only 2 solutions that mitigate all of them. There's the indirect references that are random, and there's the cryptographic references. They mitigate all of the attacks in our threat model. The time taken to verify references is pretty low for random references if they're cached in memory. If they're written to a database, then it's not quick anymore. For cryptographic references, yes, the time does go up. Memory usage is high for indirect random references. And remember, all that state needs to be shared amongst multiple servers potentially. Cryptographic references, it's low memory usage. Very little additional data needs to be stored. Identifier size, medium for indirect random references, and pretty large for cryptographic references. So relatively straightforward. So what are the conclusions? Well, there's only 2 approaches that solve all of the attacks we talked about, right? So those are the last 2 approaches we talked about. Random indirect references do require more memory, and all of that memory needs to be shared amongst app servers for stateless operation, which can, of course, cause performance issues. If you're writing all of your indirect references you're generating to the database, how much performance problems is that going to cause? Cryptographically protected references, they do require more computation time, more bandwidth on the front end. However, due to the lower memory sharing requirements, for stateless implementations, they do scale better. You don't need to share as much memory between your app server instances, just 128 bits or so. However, note that it is, or it might be easier to make implementation mistakes with the cryptographically protected references. People make cryptographic mistakes all the time, so we have to be careful around that. So our crypto implementation does need to be reviewed if that's the approach we're using. And for consumer internet scale applications that have lots of concurrent long-running sessions, the smaller per session footprint of cryptographically protected references is probably a better choice. Now, one of the things that you might be thinking around cryptographically protected references is, why do we need to share any state between our app servers at all? Right, so why not just configure one secret key on all our app servers, and then each of the references could just be the session ID and the reference concatenated together and then encrypted with my key. And, well, you need a HMAC for integrity protection. So what are the problems with that? Why do we... Sorry? You need to replicate the key, that one shared key, amongst all your servers. Okay, well, why is that a problem? Well, have you ever seen a system where you need to share a symmetric key, a secret key, amongst a large number of app servers? How often does the key get updated? Never, right? So you're introducing a key management headache. With this solution, where you have an in-session key, there is no key management to worry about. You're just generating a random key that only lasts as long as the session does, and then it's gone. So less stuff to worry about from a security perspective. So in this case, the only way we're sharing the keys between the app servers is by writing them to the database. So how we protect that on the back end is probably going to be through SSL connection to the database. We don't use a master key to replicate them throughout the servers. So yeah, I mean, there could be a potential issue with having all these secret keys in the database, but at least they're not long-lived keys. So if they were to get compromised, there would be a pretty short lifetime for which they would be valid anyways. Yeah, the critical thing with the cryptographically protected references, though, is that you do need to have the integrity protection in pretty much all cases. If you're just doing encryption, then you might still be able to modify things and access other accounts. We've actually run into many instances like that, where in one case we actually had encrypted cookies containing a user ID. Well, they were just encrypted. There was no integrity protection. So we were able to muck around with the actual cookie values. We couldn't really read them, but by messing around with them, we could access other users' sessions. So yes, we do have to be careful, even with cryptography, that we're not introducing things like that. But yeah, it does discourage. If you're seeing something long and random, it's probably going to discourage some people. Well, thank you very much.